Okay, so we are going to now use vectors to represent lines. So what we're going to do is we're going to do a bit of a throwback to grade 9. So this is a question we do all the time in grade 9. You got the point 2, 5, and we have a slope of 3 over 2. So what you would have done in grade 9 is plug in the point, plug in the slope, and solve for your b, and then get that your equation is 3 over 2x plus 2, something like that. And basically what we've done is we found that line, and the information we needed to find that line was a starting point and what in grade 9 we called a slope, but now we can kind of think of as a direction. You can figure out what a line is if you know where to start and kind of which way to go. So instead of thinking of that as a slope, I want to think of it as like a direction vector. So that would be up 3 over 2. So that would be the vector 2, 3 like that. That would go up 3 and over 2. So I can then define this line as start at 2, 5 and go in the same direction. From there, go in the same direction as 2, 3. And so how we're going to start to represent lines is this way. So we're going to say x and y is start at 2, 5, and we're going to add to that something in the direction of 2, 3. So we're allowed to go anywhere along that path. I don't want to just add 2, 3 because then that would kind of stop there. I want to be able to stretch that 2, 3 vector so I can get all the points along that line. And if I do stretch it by a negative, I'll be able to get all the points going backwards as well. So the way that we normally do that is we say plus k times 2, 3. So start at that point and then add some stretch of 2, 3, and you'll be able to get to any other point on the line. And then we always say k is a real number. So by allowing k to be any number, we can get to any point on that line. So for instance, the point, let's see, if x equals 10, if x equals 10, then 3 over 2 times 10 would be 15 plus, so we'd get the point 10 and 17 is on the line. I would get to 10, 17 by adding, so k would have to be then 4, right? 2 plus 4 times 2. So when k equals 4, we get to, doing some, that would be 8, 12, and that's how you get to the point 10, 17. So for every point on this line, there's a k value that gets you to that point. So what this is called, all of these things together is called the vector equation of line. So that's the vector equation of the line, and we're going to turn this into 3 different kind of ways to write this same equation. So that one's called the vector equation. The next type of equation using the same idea would be I'd just make a separate equation out of each of the components. So if I take just the x things, I get x equals 2 plus 2 times k, so I wrote 2k. And if I take just the y things, I get y equals 5 plus 3 times k, and then same, I'd have to state that k is a real number for kind of communication. These are called the parametric equations of that line, so we're breaking it down into its separate parameters. And then the last type of 2D equation using vectors is basically you take both of those parametric equations and you rearrange them for k. So you get k equals x minus 2 divided by 2 for solving the k equation for solving the equation for k in the x equation. And then we're going to solve for k in the y equation. So that'd be y minus 5, then divide by 3. And then since both of those things equal k, we set them equal to each other. I don't know what I'm hitting that keeps bringing the keyboard up. And this is called the symmetric equation of the line. So if you have your vector equation, you split it into two separate equations. Those are called your parametric equations. And then solve those parametrics for the parameter k, it's called. And since they're both equal to k, set them equal to each other. That's called the symmetric equation of a line. So how I'm going to write this. So we have our vector equation. And it, in general, is any point on the line xy is going to be x0, y0, which we're going to think of a starting point, which could be any point on the line. So vector equations can look very different. So I could then, so we know 1017 is on the line. I could rewrite this equation to be 1017 there, and that would be the exact same line. You can pick any point on the line as that starting equation. So that doesn't change the line. And then plus k times d1, d2, I'm going to call it, and d1, d2 is any direction vector, so any vector pointing along the line. You can kind of think of it as like the slope vector, because that's kind of where we got that one from. So that could be 2, 3 at the end, but I'd have the same line if I made it 4, 6. If I made it -2, -3, any scalar multiple of that would work. So any point on the line for the first part can work, and any scalar multiple of a direction vector would work for the second part. So that's called the vector equation. And then the parametric equation would then be x equals x0 or x0, if you want to sound fancy, times d1 plus k, d1 times k, sorry, and y is y0 plus d2 times k. Those are your parametric equations. And then finally, solving both of those for k and setting it equal to each other, you get x minus x0 over d1 equals y minus y0 over d2. So that's called our symmetric equation. And they all kind of flow from one to the other. You can turn any of them into the other ones if you understand the connection. So you can take the two parametrics and rejoin them to make the vector equation again, and so on and so forth. If you start with symmetric equations, you set each one to a k, and then you rearrange to get x by itself and y by itself. Then you got your parametrics. Then you could go and make that into a vector equation. Now that's 3 ways to write the equation of a line, but we also have the grade 9 way. And the grade 9 way, one thing that we did in grade 9 was we did what was called standard form. So that would be then just rearranging my y equals mx plus b. We called something like that standard form. Often you would multiply everything by 2 to get rid of that fraction. Let's just make sure that I've done this right. And there's our standard form version of that line. And what we're going to call that now, we're not going to call it standard form anymore. We're going to call it the scalar equation of the line. And it's ax plus by plus c equals 0, something like that. That same equation we would have done in grade 9. And then what I want you to see is the a and the b are 3 and -2. And that kind of reminds me of my direction vector. But I'm going to look at the vector 3, -2. So just taking a and b by itself in my picture. So that would be going over 3 up to, sorry, down to, and I get kind of this vector. And I've tried to draw it to scale as best I can, but I hope you see if I kind of extended, that would be a right angle. And we can in fact prove it's a right angle by doing that vector dotted with the direction vector 2, 3, and you get 6 minus 6, and you get 0, which means that, yes, A and B is actually perpendicular to the line. So AB is what's called a normal vector to the line. It's a vector perpendicular. So where AB is normal to the line. And so back in grade 9, you had standard form, and we said, standard form, kind of useless. You can't see the slope, you can't see the y-intercept. It doesn't tell you anything really about the line. You have to rearrange standard form to get y equals mx plus b. Well, now we can at least say, and now that we're all the way in grade 12, we can say, well, it doesn't tell you nothing. It tells you a vector that's perpendicular to your line. So those first two terms are going to be perpendicular to your line. Okay. So armed with all that information, see if you can take a swing at some of these 3 example questions here. So you can pause the video, take a swing at them, and then we'll talk about 3D lines in a second. Ooh, we got more ground to cover. Told you these lessons were longer. Okay, so find the vector, parametric, and symmetric equations of a line that pass through these 2 points. So in order to get a vector equation, I need a starting point and I need a direction vector. So for starting point, I've got 2 choices. I can pick 5, 3. I could also pick negative 2, 4. I'd get the exact same line. For direction vector, if I call that A and that B, I need something that points along the line. So neither of those are both points. They're not vectors. To make them a vector, I could connect those 2 points with, say, the vector AB, which would be B minus A. So get a vector that actually points along in that direction. So negative 7, 1 would work when you do B minus A. So that would work for a direction vector. And so that I don't lose communication marks, I'm going to say K is any real number. And then any scalar multiple of this would also work. So I could do positive 7, negative 1. I could do positive 14, negative 2, so on and so forth. So you can stretch this vector in any way. So that's how that back end can change, and you'd still have the same. And this could be any point on the line. So 5, 3, or minus 2, 4. You could use any point on the line, but those are the 2 most obvious choices. So there's my vector equation. For parametrics, I'm going to break my vector equation into parts. And then for symmetric equations, I'm going to take those parts, rearrange for k, so it's going to be x minus 5 divided by negative 7. And then y take away 3 just divided by 1, so I could just do y take away 3 like that. So that's a perfectly acceptable answer. Often what you'll see, and you got to watch out for this, if the denominator is negative, often what you'll see is they make that negative and then they flip the subtraction. So basically I'm multiplying the top and bottom by negative 1 and it becomes negative x and positive 5, and they write the subtraction in the other way. So you don't have a negative x at the front. So you just got to look out for that. If you're starting with a symmetric equation, I'll often do this in the question, and you have to realize that your direction vector isn't a positive 7, it's a negative 7. So you have to kind of, if I start with that, I always write out equals k and then solve for x. And since there's a negative there, you're never going to get the wrong answer if you do it that way. But if you're trying to jump right from that to the answer, that's when you can make mistakes with that minus sign. But on a test or whatever, I would take the first version with the negative on the bottom. No problem at all. Find the equation of a line that passes through the point 3, 4, vector equation of a line. Okay, so it's giving us a starting point. So the only thing we're missing is a direction vector. And we're perpendicular to this line. So what I need is a vector that's perpendicular to that line. Well, that's a scalar equation of a line, we're going to call that. And I know that the vector AB is, in fact, perpendicular to the line. So I can fill in that and say k is any real number and be done. So since that AB is a normal vector to the line, I want my direction to head I want my direction vector to be perpendicular to that line, so I'm going to use that vector as my direction vector. Okay, so find the scalar equation of a line that has a direction vector. So the direction vector is 4, -5, and we're trying to find the scalar equation. So we're trying to get that normal vector. We want a vector that's perpendicular to the line to make the scalar equation. So the quick way to do that is you switch, it's the same kind of idea, as like negative reciprocal. So this as a slope would translate to that. You're going down 5 and over 4. If you want a perpendicular slope, you flip it and change the signs. So here you switch the order and you change one of the signs. You don't want to change both because that would be the equivalent of doing that, and that wouldn't be perpendicular it would be the equivalent of doing that, and that wouldn't be perpendicular anymore. So one way to double check that you have chosen a perpendicular vector is do a quick dot product. 5 times 4 is 20. -5 times 4 is -20. Those make 0, so I have in fact found my perpendicular vector. So that's my A and my B. So my scalar equation is going to look like 5x plus 4y plus some c value equals 0. In order to find that c value, we're going to use the point x and y. So 5 times 4 plus 4 times -2 plus c equals 0. So that's 20 minus 8 is 12. So c is going to be -12 when I bring that over. And so my scalar equation would look something like that. Okay. If this was a 3D picture, so now we have a line cutting through 3 dimensions, so huzzah. We could use that same kind of idea. We could have a starting point and then know which direction ahead, and we'd stay on that line. So your vector equation now has 3 parts to the point. We still have a starting point, and we still have a direction vector. Sorry, I was using D's, D1, D2, D3. So that's still, everything kind of looks exactly the same. You end up with now 3 parametric equations, x0 plus k times d1, y0, I think I was writing that in the other way, d1k plus d2k, z0 plus d3k, something like that. And then you end up with the symmetric equations are the exact same idea, but you end up with 3 of them. So you set them all equal to k and set them all then equal to each other. So that's the symmetric equations in 3D. Again, k is a real number. So you got your vector, your parametrics, and your symmetric. So find the vector, parametric, and symmetric equations of the line that passes through these 2 points. So again, I'm going to say that's A, that's B. For a direction vector, I can do B minus A and get 9, 4, and 9, I believe, if I do B minus A. So my line is going to look like, and again, you can pick either one of the points as the starting point, and then B minus A or A minus B for your direction vector. So there's my vector equation. Break it into its parts. There's my parametric equations, and then set each of them, so solve each of them for k. So it's going to be x minus 3 divided by 9 is the same as y minus 4 divided by 4, which is going to be the same as z now plus 2 divided by 9. There's my symmetric equations. So exact same problem as this one, the first one we did in 2D. Now we've just got this third component to it. Exact same steps, nothing fancy. Okay, find the vector equation of the line that intersects the line blah on the xy plane and intersects the line blah on the xz plane. So we're basically being told, I think I was normally drawing them like this. So we've got two lines involved. One of them, we're going to be worried about the xy plane. So we're going to find a point on the xy plane from the first line. So I'll just draw a line through that point. And then on the xz plane, so that would be then sort of this wall, we're going to get another point from line 2, whatever it looks like. And then our line is going to connect those two dots together. So this will be the line that we're trying to find. And so we got to go way back to our first 3D lesson. I know that if that point's on the xy plane, it's got a z value of 0. So I'm going to take the parametric equation for line 1 and figure out what makes z equals 0 on line 1. So if I look at the z equation, it's z equals 4 plus k. I want z to be 0. So I know k equals -4. And so that point, the point on line 1, is going to be -1, 2, 4, -4 times 2, 4, 1. So just making k -4 and solving, and I get -1 take away 8, so -9 for x. I get 2 take away 16, -14 for y. And then 4 take away 4, I do in fact get 0 for z. So there is our first point. So that's this point here in our picture. For our next point, line 2, it's on the xz plane, and the xz plane for sure has y equal to 0. That's what the xz plane is going to do. So I'm going to solve for what makes y 0 on the xz plane, and I get the y is 2 plus 4t. I was nice and chose 2 different letters for the lines because they can be, I'm not going to necessarily get -4. So whenever you have 2 separate lines in the same question, you need to have a different parameter variable. So k for the first one, t for the second one, because they're not necessarily the same. But again, y is going to be 0, so 0 equals 2 plus 4t. So t is -1/2. And then I'm going to solve for that full point then. So x, y, z equals, on that, it's going to look like 0, 2, 3, -1/2 times -2, 4, 1. And so I'm going to get the point 0 take away, that'll be +1, so that'll be, oh, +1. I said it, I didn't write it. So -1/2 times -2 is +1, so 0 plus 2 is 1. And then 2, and then we're going to do -2 times 4. Sorry, -1/2 times 4 is -2. So we get 0 for y, that's what we were going for, that's good. 3, and then -1/2 is 2.5, so 3 is, so 5/2, if we want to write it as a fraction. And then what we're doing is we're going to make the vector equation. So maybe I'll call this point A and this point B. So that's A, that's B. We're going to get the vector equation of that line. So we need the vector that connects A to B, which again, we're going to do B minus A. So 1 take away -9 is 10. 0 take away -14 is 14. And 5/2 take away 0 is 5/2. There's my direction vector. We just want this is a long question. We just want the vector equation. I don't have to get all 3, thank goodness. I can pick either one of those points as my starting point. So I've used T and K, so I'm going to use G. It's a great letter. So that could be potentially one way to write the equation of that line. You might have used the other point, so you might have used 1, 0, 5 over 2 for your starting point. And as long as your vector is a scalar multiple of my vector, then you've got the same equation as me. Okay. Last one. We're going to decide whether these lines are the same line in disguise, parallel to each other, or none of the above. And I can see right away that the direction vectors are scalar multiples. So they are definitely either the exact same line in disguise or parallel, because they're heading in the same direction. So our two options are, I'm starting at this point and heading this direction on this line. The other line, it could be a different point, and I'm heading in that direction, so on a different line. So they might be parallel, or they might, in fact, be the exact same line drawn on top of each other. And what we need to check then is if this point is on the first line, then they're going to end up being the exact same line, because as long as they have 2 points in common, since they're going in the same direction, if they have 2 points in common, then they're the exact same line, because we know they're going in the same direction. If they're different lines, then they're not going to have any points in common. So what I'm going to check, if this point is on line 1. And so one way to check that is, let's just figure out what k would have to be to make, say, the x work. So to make the x work, it would have to be -3 would be 2 plus 3k. That would make, so that's using the line 1 equation and setting it equal to the point of line 2. And so I get k is -5 over 3. So if it's going to work, k has to be -5 over 3. And if I check the point on line 1 that has that value, -5 over 3 times this vector, I get the point. So -5 over 3 times 3 is -5. 2 subtract 5 is -3. So the x's match. -5 over 3 times 12 is -20. So 1 take away 20 is -21. -1 take away 20 is -21. And I see already that that's different than the 0. So I know that I'm getting a different point here. So I know that these are, in fact, parallel lines, but I'll finish the question. -5 over 3 times 6 is -10. 4 subtract 10 is -6, which is not the point that we were looking for. Therefore, they are parallel. Same direction, because they're scalar multiples, but different points. Okay, so for your formula sheet, I want you to add the 4 ways to write a line in 2D. So vector, parametric, symmetric, and scalar. And there's 3 ways to write a line in 3D. And you'll say, Mr. Clement, you didn't talk about scalar equation. And that's because there's actually no way to represent lines as a scalar equation in 3D. There's just no possible way to do it. You have to use vectors to represent lines in 3 space. And you're like, well, what about, wouldn't it just be this? Everything has been just one more letter whenever we have 3D. And yes, that is a 3D scalar equation. But what we're going to see in our next lesson is that's actually an equation of a plane, not of a line. So there's no way to make a scalar equation of a line in 3D. If you have that type of equation, it doesn't make a line. All the points that would work on an equation like that form an entire plane, an entire flat surface, not just a straight line. So explain the different parts of a vector equation of a line. So talk about a starting point and a direction vector, and the variable goes with the direction vector, and explain how to use the vector equation to turn it into the other two. Those are the notes I want you to make to yourself, and then we'll work on practice when you're in class.